Hi everyone, this is Pascal from Kaplana. Pleasure to be here at Gore. Thank you also, Stefan, for hosting this session. I'd like to talk to you today about very deep language models and their applicability in verbatim coding or open-end coding, open-end analysis. Yeah, I'm sure you're familiar with the task. Yeah, so I'd like to start off with a brief introduction in NLP, natural language processing progress over the recent years. Let me just put my face up here. My, let's say, history with natural language processing, also that of our company, started in the early 2010 years. And back then, it was still a lot of, the process was more like always training on specific labeled data and then applying this to unseen data. And the technology changed a little bit, but really the big revolution came when people started to realize that you can actually leverage the whole of the internet or subset of it, a lot of text data, to actually generate a model that understands language patterns in language really well without any labeled data. And sort of this is what came up in around 2017, 2018 with Elmo and BERT and all these kind of acronyms I don't want to explain here. It's also not relevant, but really this the model started to become bigger, and then also people started doing training on labeled data to really also leverage these huge models. And how they did this is with unsupervised pre-training. What is this? So pre-training already mentions it a little bit. It's like a stage you do before you actually build a model, let's say, for the specific task, let's say for open-end coding or for sentiment analysis or anything really. So you do this before with the exact same architecture. So, and what typically we then use is you go ahead and take Wikipedia or really large internet scale data and feed this through your model with a specific formulated task. And the task is usually just like, or often it's, for example, this masked language model task, which is basically like in school you have a sentence and then one word is left out and the model has to predict which one is missing. And then also obviously has the correct example and then can learn from these kind of samples. And this is done over gigabytes of text. So with this we're able to generate a generic language understanding, also maybe already on the specific domain. And you can make sure that you also include, let's say, social media data if you want to then work on social media or anything really you want. And that is available, obviously. So this then has the advantage that you then need much less of this. You need much less labeled data if you do this unsupervised pre-training, because you already give it a lot of understanding by just feeding it tons of unlabeled text. So we at Kaplana, we deal with this open-end coding, and we develop AI for these tasks, meaning just assigning topics, codes, sentiments, tones, etc. to verbatim responses. And we try to always stay ahead in the curve, and we also used such a large transformer model. More than 100 million parameters, really big. It doesn't run on a normal machine, runs only on GPU and TPUs. So really a state-of-the-art model. And we trained this on Wikipedia and other public data sources in multiple languages. And then we took this model and exactly this model, and then the second stage training process, where we just take our database of reviewed responses, our customers of Kaplana.com review for most of the studies. They review a couple of responses by hand, and the rest is predicted by the AI. So out of these proportion that a hand review, we can then actually learn, fine-tune the model for the specific task. And then once this is complete, then we also train a little bit on every customer study. So if a customer then uploads a new study, I don't know, even it can be a completely different topic, then we fine-tune based on what he or she reviews on the platform. Yeah, why do we actually need these large models, or does it really make a difference? So we started off with, in 2016 or so, with these simple models, as we bag of words, and in our internal test set we got around 55% F1, a metric I'm going to explain a bit later. And then we made progress. We went into long short-term memory networks with word embeddings that improved things. These word embeddings are already learned then on a lot of data, not like internet scale data, but significant amount of data. But then really the big jump was with the transforming models, which we were then able to use since since mid-2018. So, and besides accuracy, very much more accurate than the basic models, there are more advantages also, such as, for example, zero-shot capability. So it learns the meaning really of these codes and the text. So you can, for example, so it would automatically, without having anything reviewed, without having labeled data, it can assign this completely new code to this response. And you can also rephrase it and still understand that this is the same meaning and assign it to the same response. Also, because it's, you can make it multilingual, which ours is, and that means it can reason a little bit across languages. So for example, for this code, it's in English, but it understands this roughly the same meaning as the corresponding English response. This is not a translation model, but it can reason across languages. Yeah, we usually use the F1 as a measure of accuracy when we do our experiments. Also, we communicate this to the user, how good is the agreement between what you reviewed and what our AI predicted. And the advantage is that it's quite robust towards label imbalance. In this case, some codes are much more frequent than others, and so it's really important that a metric is robust towards this, and this is why we also choose this F1 metric. And it's also comparable to literature, etc. Yeah, so we took then this model and deployed it on our platform. So this is what's running since, again, mid to end 2018, with obviously since then a few improvements, but sort of since then we've been running such a model, and a couple of agencies have made experiments where they compared human coding versus what we can do, what is the agreement between human coders, what is the agreement between human coder and Kaplana, and also compared it with other tools. You can see here one other online machine learning self-service tool, which then has a quite low score, and we and the humans have much higher. We have even higher scores here than the humans, because we're able then to reproduce what a specific human does much better. So we learn from, let's say, human coder 1, and then we apply the learnings on the rest of the data, which also this person coded. So it just measures sort of consistency of the coding with what the human did, this specific human did, and so we're able to get much more consistent results than if you would code with 3 different people and then just, let's say, average this or something, or just take one of them, let them code different subsets, let's say, of the data, which typically you would have to do if you do a large study. You would have to have multiple coders, and then you see that the agreement is quite low. And if you use our tool, you can actually get much better agreement by just letting one person review some responses and then letting the AI do the rest. So here, these were quite cool results we got on these Portuguese and English verbatims, also really complicated verbatims that were telephone interviews transcribed. Really long, a lot of topics, a lot of codes, very open, which is also why you see these quite low agreement scores, let's say. Similarly, for another study we did with the Dutch research agency, which just had 2 human coders, professional coders, and they achieved around 62 in the way they found an agreement. And if we look at what the agreement is between Kaplana and the coders in each individual coder, it's more like 65. So also slightly better, which is great. And we also sort of, this is why we're comfortable saying that we do achieve human level accuracy. This doesn't necessarily mean that in every case we do that. Obviously, these were cases where they did review a significant amount of responses. Typically, we see that for the first, maybe I jump back for this slide. In the first couple of responses here, you see actually the learning curve of one of our models. So here you see what the range of what we would get from a human coder, and in the beginning, we might be below for a complex study. But then quickly after reviewing a few only responses, you get into the terrain where it's actually comparable to what humans would get. So really with very few training samples, we're able to get very accurate results. And this is also what's running on our platform. And yeah, people are really happy with these results. We also took a look at what happens when you then do analysis on top of these results. So this is, for example, for driver analysis. Success Drivers did a study where they compared also versus manual coding or versus the other tools, and they just saw that it's actually significantly better with our very sophisticated and very deep language model. Yeah, so that's already, I think time is already up. Yeah, I hope this was interesting. Maybe I like to conclude with that we really think that these very deep language models are the future. Maybe they don't have to have that many parameters in at some point, but at least for now, it's a clear trend. The more parameters, the better, and they will just get more compute hungry and better over time. We're very excited about this technology, and we baked it into our platform, kaplana.com. You can try it out if you want to, benchmark it also to other solutions, to Human Coder, to see how it makes you much more efficient in coding open-ends. With that, I'd like to go to Q&A. Thank you very much for listening in, and talk to you soon. Bye.